Multimedia talk by Amitai Zernik, and we'll talk about trivial and interesting relations from fixed-point localization.
Okay, so thank you all for coming. I want to tell you today how you can derive relations from fixed-point localization. So let me start by kind of briefly recalling what the fixed-point formula says. Okay, so let G be a torus group. And let M be a closed-oriented manifold with a G action. So the fixed point formula says that if eta is an equivariant form, I'll say what that means in a second, the integral of eta over M is equal to the sum over the connected components of the fixed points of M of the integral of over f of eta divided by the equivariant Euler form of the normal bundle of f sitting inside M. So what do I mean by an equivariant form? That's just an element of the following complex. So it's the usual complex of the Ram forms on M, but with values in the polynomial, the graded polynomial ring generated by alpha 1 through alpha m, where the degree of alpha I is equal to 2. Sometimes you will also need to look at to invert some elements in this ring, so you can think of rational functions in this ring. And it turns out when you restrict to the G invariant elements, then you have a differential acting on this, and that's what I mean by this is the Cartan-Weil differential. It's a kind of deformation of the exterior derivative, and that's what I mean by a closed equivariant form. Yes?
For people who don't know this word, is there a concrete manifold and concrete reaction that you can tell us?
Yeah, I'm going to give an example in just a second. But let me just say that the motto of this talk, before I give the example, is that sometimes you can get interesting things on the right-hand side, even when the left-hand side vanishes for some stupid reason. And my favorite stupid reason is that, maybe I'll keep that here. My favorite stupid reason is that the dimension of M, probably want to say it like this, the degree of eta is less than the dimension of M. So the left-hand side vanishes, but of course the right-hand side, the fixed points have lower dimension. So they might even be isolated points, as we'll see now. So now we come to the first example of the talk. Okay. So let's start with a toy example. Consider the diagonal action of the torus group on C to the n plus 1. Okay? And I'll take M to be the projectivization of this. So that's just CPN with some torus action. This has n plus 1 isolated fixed points. So the ith fixed point in coordinates is obtained by just plugging in 1 at the ith coordinate. Right? So this is for I going from 0 to n. And let's take as our eta to be, well, the Euler of the dual to the tautological line bundle, the equivariant Euler. But you should really think of this as some form representing the equivariant hyperplane class, or an equivariant hyperplane class. Okay, so what does the fixed point formula say in this case? Well, it says that the integral, so we'll look at the integral of eta to some power r over M. That should equal to a sum over the fixed points, right, going from 0 to n. Here we'll have alpha I to the r. That's just a restriction of eta to the r, to this fixed point pi, divided by the product over j not equal to I of alpha I minus alpha j. So that's, in this case, the Euler of the normal bundle, or the tangent space to the point pi. And we know what we expect to get in some cases, right? So if r equals n, we expect to get just a classical integral, which in this case is the intersection number of n planes in CPN, which is, of course, just one, just a single point. If r is greater than n, then we get something. We get some symmetric polynomial in the alphas. But this talk is about what happens when r is less than n, and, well, you get 0. This is actually relation number 1. So we see that we have some sum of rational functions that vanishes. OK. Now let's go into a more interesting example. Maybe I'll use this board. So let's take M to be the moduli space of holomorphic disks. So here, these are homomorphic disks sitting inside CP2M with boundary on the Lagrangian RP2M. So the picture you should have in mind is the following. So you have this disk living inside X, and the boundary of the disk is constrained to lie on the Lagrangian. And this disk has K boundary markings and L interior markings, and beta here is the energy or the degree. So you get something like this. And now, so the localization formula in this case is a bit more complicated because the space M has boundary and corners. So in order to deal with that, we need to kind of introduce these A infinity type resolutions. Anyway, the fixed point formula takes the following form. So we have sum over C greater or equal to 0. So let me write the formula and then say a few words about it. OK. So I don't want you to worry too much about the details of this formula. I don't have time to explain all of them. But let me at least tell you what the kind of domains of integration are.
What is the action?
Say again?
What Taurus action do you?
Oh, OK. So I look at the action on RP2M that rotates pairs of coordinates. So basically, I can think of it, and this extends, of course, to. OK. So it's known that the boundary of M is a disjoint union of fiber product of simpler moduli spaces. So let me draw this like this. The boundary of M is equal to a disjoint union. Let me just draw the energy of these disks. So these are fiber products that parameterize pairs of disks which are connected by a node on the boundary. And the space that I denote by tilde partial of M is the same disjoint union, but now I allow the disks to kind of replace the fiber products by products, which means that I allow the disks to move kind of independently of one another, and I get this sort of disjoint union. Okay? And finally, the space that I denote by boundary check is obtained by the same disjoint union, but now I forget the node or the node marking on one of the sides. So you may ask, well, which side? So it turns out there's a natural way to orient or to order these factors, and you can think of this as having an edge from this vertex to that vertex. And when I write here, when I write this to the power of c, I just mean that you use Leibniz to iterate this. So you can see that you get a sum over trees with these edges. So right, you might get this is the first edge, and then maybe you apply, this is the first edge, and then maybe you apply this operator again to this moduli factor, and you get a second edge, etc. So you get a sum over oriented labeled trees. And it turns out you can have a fixed point formula with all of these trees, but it's better to do some kind of resummation to avoid some singularities introduced by the diagonal here. I don't have time to talk about it, but then bottom line is you get this, you would restrict to this Clopin component of this sum over trees, of this disjoint union over trees, correspond to even odd trees. These are trees that are alternating between even degree and odd degree factors. And then you really take the fixed points. So then you really sum over just the fixed point components of these kind of products of moduli spaces. And what does that look like? So let me draw an example of what a fixed point component might look like. So for each even factor, right, even degree factor, it turns out that the disk component has 0 energy. So it looks, I draw it flat like on the Lagrangian. Of course, it may have additional components connected to it which have positive energy. So it might look like something like this. And then maybe here there's another component connected by another 0 energy closed component. So it looks something of this form. Maybe you have more spheres attached here. And then you have some markings, some incoming edges which introduce boundary markings and maybe part of the k markings you begin with. And then you have some odd factors which I will draw like this, some positive energy odd degree disks. And they, of course, can also have some components attached to them. So that's the basic picture of the fixed point locus. And what can you do with this formula? So one thing you can do is interpret the left-hand side, or specialize the left-hand side to count real planar curves. There's a well-known signed count in tropical geometry due to Welchanger. And so this formula gives another way to compute these invariants. Another thing you can do is interpret this as encoding the structure constant of the equivariant Fukaya endomorphism algebra of RP2M sitting inside CP2M. This is not trivial because we're working over a kind of non-orientable version of the Novikov ring and not the field. Anyway, these two things I don't want to talk about. This talk is about relations. So another thing you can do is play the same game we played before and just see what happens when this vanishes for the same stupid reason. The degree is too low. And so sometimes you, again, get isolated fixed points, which means that this right-hand side is just a sum of rational functions. And this is actually the example in relation 2 here. So I don't know if I mentioned the relation 1 we already covered. The relation 2 is this sum of rational functions. And just as an anecdote, I was interested in this. I was looking for this relation because it's sort of some subtle sign computation said that there should be a sign factor corresponding to whether RP2M is pin plus or pin minus. And so that should be some dimension-dependent factor, and this is that -1 to the n plus 1 that you see on the second line there. So with some confirmation that it works. But then, of course, it really gets interesting once you add more points and more energy, and then F starts having interesting topology. Where does the topology come from? Well, the topology comes from these configuration spaces. So the positive energy maps are all rigid.
Points. In that case, is the identity provable comparatively?
So I don't know. I mean, I checked it. I mean, it's an interesting question. I did verify it until I was sufficiently convinced that it was true. So here's, so what I was saying is that the positive energy components are all rigid, but you do have some interesting topologies just from configuration spaces of these 0 energy disks and spheres that you see appearing here. And it turns out that the integrals you get here are what are known as descendant integrals. So in the closed case, these are well known, and they contribute these multinomial factors that you can see on relation. I don't know how much you can see, actually, but here you have these. Do you see anything? Anyway, here you have some multinomial coefficients. It's really mostly just for kind of get an impression. But there are also some brackets here with superscript O. These are the descendant integrals of disks. And these were developed or kind of defined and computed in a recent paper from 2014 by Pantari Pandey, Solomon, and Tessler. And it's kind of cool that these integrals also appear in this localization formula. And in fact, you can derive enough relations from this localization formula to completely determine these these integrals. OK, so I think I'm kind of running out of time, right? Maybe I'll just say two more things very briefly. One thing is that in higher genus, the story gets even more interesting. So the space M becomes a Kuranishi space, and a lot of the transversality arguments kind of break down that were used to prove this formula. But you can still kind of formally write this formula down, a kind of natural generalization of this formula. And these relations allow you to get some evidence that it's really working, that non-trivial evidence that it works. And the second thing I wanted to mention was that I would be very interested in seeing a kind of categorification of this. What I mean by that is replace this equality of numbers or invariants by a quasi-isomorphism of infinity algebras or categories. Part of the proof is actually already of that form, but it would be interesting to do that. I think it would have interesting applications, also to mirror symmetry. So I think that would be a good place to stop. Thank you.